It's amazing to see you all here. I'm Aleksa Bjelogrlic, and it's my first time speaking at a conference, and my first time at TEARDOWN, so be gentle. And as much as my inner theater kid loves being up here, I'm also a little terrified. But we've got no time for that. This talk covers mostly the project stage of things, not the juicy product bits. But I'll do a talk on that once it's on all of your lab benches. So hold your questions to the end and enjoy the show. Before we get all technical, let me tell you how I went down the dark path of test equipment. So I'm an electrical engineer by day and an electrical engineer by night. And ever since I touched an Arduino for the first time, I've been fascinated by oscilloscopes. This was my first scope. 2 channels, 20 megahertz. It was given to me by a prof I learned a lot from as a kid. Shortly afterwards, I watched a video that put a thought in my head that I couldn't shake out. I learned what was inside the mysterious electronic signal box that I had longed for so long. And then I stumbled upon Bunny's oscilloscope module for his Novena laptop. Dear audience, this changed everything. Video? It works. No audio, okay. The Novena had an FPGA coprocessor tightly coupled to its CPU, which was used alongside a high-speed ADC and a front end housed inside a probe, actually, to make an oscilloscope. This tight coupling from FPGA to CPU had me thinking, and after a few back-of-the-napkin sketches with my friends at the university pub, I ended up with this. I became convinced that with a fast enough link, it would be possible to transfer every sample from the ADC to the user's computer in real time, with all the triggering and processing being done by the CPU. Now, I know that sounds exactly like the setup to Glass Onion 2, but I'm releasing everything as open source. So the only mystery here is when I'm going to get to the juicy technical bits. The good news is you don't have to wait much longer. Through a rigorous process of TED Talkification, I've compressed 5 years of development into the next 20 or so minutes. First things first, what is an oscilloscope? Actually, I'll spare you the history lesson. What is a digital oscilloscope? You can think of it like using a voltmeter to measure voltage billions of times per second. This process is called sampling. And the number of voltage measurements, or samples per second, is a band or oscilloscope spec called sample rate. Right up there. This is normally spec'd in gigasamples per second and is determined by the analog to digital converter used in the oscilloscope. That's the ADC. The maximum bandwidth is ostensibly a function of the sample rate of the ADC by Nyquist's theorem. Don't fall asleep on me yet. But practically, we leave a little wiggle room for the anti-aliasing filters to avoid signals haunting us from beyond the Nyquist threshold. And sometimes high oversampling points to the analog bandwidth as a limiting factor. Sample rate is getting cheaper and cheaper, but good analog parts are still expensive. Speaking of analog, the level of precision of the ADC generally corresponds to the number of bits it converts the samples to. This number of bits is the scope's resolution. After the scope takes a sample, it gets sent to a memory buffer, the size of which is another spec called memory depth, usually specified in points, which is just a vertical resolution agnostic unit that is equivalent to megabytes for an 8-bit scope. Most scopes would fill this buffer in milliseconds. So for long captures, they just turn the sample rate down until it gets filled slower. This trades off bandwidth, meaning you'll start losing signal information as soon as the scope does this. Deeper memory delays the trade-off. On the other side of this buffer is the trigger. Whenever a certain condition happens, usually a rising or falling edge, the scope displays what's in the buffer around the trigger point. Processing and displaying the trigger data is slower than the trigger itself. So there is some dead time between displaying waveforms, which will miss some data. To lower this dead time, you want a scope with a high waveform update rate spec, which reduces the likelihood that you miss any important glitches. Since waveform update rate can go up into the millions, and our fleshy meat sensors don't, these waveforms are drawn on top of each other so we can easily see any outliers. Also drawn on the screen are these lines called reticules. They separate the screen into horizontal and vertical divisions. What amount of time and voltage each division represents is set by the user. Increasing time per division results in fewer waveforms per second as more samples are displayed. This takes a lot of processing. Changing the voltage per division physically sets the gain and attenuation on the scope's analog front end, much like a manually ranging multimeter. The analog front end has to feed the ADC the one range of voltage it accepts. Go too high, and you clip the signal. Go too low, and the ADC's effective resolution plummets. The front end can also AC or DC couple the input signal, or shift the signal up or down by injecting a voltage offset. The input impedance of the front end should be 1 megohm in parallel with 10 to 20 picofarads of capacitance to support standard oscilloscope probes. Some scopes provide a 50 ohm input option for active probes or connections to other 50 ohm systems. I'm just going to lump all these requirements into signal conditioning. So these are the main specs you need to consider when designing an oscilloscope. If you have all of these, you can bend reality to your will. Not much of a laugh since someone else already did it, eh? Or make electrical test equipment. But I didn't want to make the same kind of scope as the big companies, but open source. I want to stream all the sample data to the user's computer. But why? This brings memory depth up from tens of meg points to, well, as much RAM as you're willing to throw at it. Likewise with waveform update rate and your processing power. And since everything is done in software, you can easily add custom triggers, protocols, and other features. Like anyone with a collection of old test equipment, some say a hoard of old test equipment, I know the analog stuff stays pretty much the same throughout the years, but the digital stuff is what doesn't keep up with the times. So fundamentally, the idea is to put all the good analog stuff in a box and offload all the digital stuff. This should make a scope that's never obsolete. Will actually get better as you upgrade your computer over the years. At the start of any long design, you want to define what specifications you're targeting. The limiting factor for sample rate and resolution is how fast we can send the data over to the host computer. That speed, or throughput, needs to be faster than the sample rate times the resolution. So where do we start here? I want to make something on par or better than the scopes that are really popular in the community today. To do that, I need at least 1 gig sample per second at 8 bits. That's 1 gigabyte per second of data. And looking at USB 3 chips that are publicly available, none could come close to what I needed. What I needed was a chip that used USB 3 Gen 2, which didn't exist at the time. However, one was on Cypress's product roadmap, so I decided to do a proof of concept with Gen 1 and upgrade later. The ADC I chose splits a sample rate across its 4 channels. Many scopes using this low-cost ADC build their front ends to the bandwidth resulting from the lowest sample rate. To give the user more flexibility, I'm targeting the highest bandwidth this part can reasonably offer. I took many of the signal conditioning requirements from benchtop scopes. It had to accommodate a very large range of voltages, provide AC or DC coupling, an adjustable voltage offset that worked well on all ranges, and the right impedance for scope probes. Oh, and throw a 50 ohm mode on. Why not? With all the specs set, it was time to make a prototype. I chose a modular approach and tried to make every module individually testable. Skipping forward in the timeline, here's the finished design. It ended up looking a lot like my first sketch. Before I embarked on designing the front-end modules, I put together a spreadsheet to figure out what gains and attenuations I needed to use for each range. The first module I designed with was what I called the front of the front end. This is where the termination, coupling, and attenuators lived, alongside the high impedance input buffer. Testing found that it worked with no attenuation, but it had peaking in the frequency response. Worse yet, it would oscillate rail to rail if either attenuator was activated. I thought the problem was that I was using just the one really fast op-amp. So in the span of one evening, I decided to give it a little op-amp helper. And promptly learned why you don't rev a board in 6 hours. So I resolved to figure out a proper solution later, use Rev 1 without the attenuators for testing, and move on to the next module. To complete the front end, this board needed finely adjustable gain, DC offset control, Nyquist filtering, and an ADC driver. That sounded like a lot of work. Luckily enough, the Novena scope schematics introduced me to just the right parts for the job. The LMH6518 programmable gain amplifier, or PGA, and the DAC 101 digital to analog converter to generate the offset voltages. This board attached to the front of the front end, and the 4-to-1 adapter that'll take all the signals to the ADC. That fancy connector was also a lot harder to test with. So I made a breakout board and got to testing the PGA. The frequency response was unaffected by the 900 megahertz rated PGA, but I did learn of a flaw in my planning spreadsheet. Although the PGA was supposed to drive the ADC directly with about 1.8 volts, it wasn't able to drive more than 0.9 volts during testing. This was, of course, in the PGA datasheet. Having learned my lesson at that point, I took some time to really read over the ADC's datasheet to see what could be done about this. And I found out it had built-in digital gain, which could be used without losing any appreciable signal fidelity at a 0.8 volt input. There isn't much interesting to see here, just regulator, I/O expander, and a lot of connectors. And then the ADC board had a lot of diff pairs on it, but not much else. I added a connector for an external clock since I was going to be using a lower sample rate anyway, and didn't want to redesign the clocking circuit once things sped up. And since I learned to read the datasheet, I used its recommendation for terminating the inputs. And that didn't work. This caused some weirdness in the frequency response that went away once I just replaced them with a 100 ohm resistor across each input. The next board up would take the ADC data and send it through USB 3. Unfortunately, I couldn't just connect the ADC to the USB 3 chip directly. I needed an FPGA to convert the 8 LVDS data pairs from the ADC into the 32-bit parallel bus for the FT601. I chose the smallest, cheapest one that I could actually do the full ADC speed eventually, a Spartan 6 in a hobby assembly-friendly TQFP package. I also included a USB 2 chip that served as a low-speed side channel for FPGA configuration and issuing commands to the rest of the scope. And as you can tell from the blobs of superglue and wires, I made some pin swap errors. Normally, that would be fine for an FPGA, just map the pins elsewhere. But both of these swaps were in the configuration part of the FPGA, which is the only place where you can't remap the pins. Once I was able to flash the board, I realized that I just backed myself in a corner where the only way out was to learn an HDL language, and I chose Verilog. After half a year of trial and error, I was not a veritable Verilog veteran, but I had a working design that conceptually looked like this. High throughput data flows from the ADC to the left to the FT601 on the right. And all the hardware control commands came in through the FT2232 on the right and got converted to I2C or SPI and flowed to the front end and ADC on the left. With the whole thing assembled, it was time to start writing all the software I had planned. I planned out the software, right? Huh. Thankfully, I had a powerful tool at my disposal, giving cool hardware to my friends. We all had our fourth-year university Capstone project on the horizon, so we agreed to make this oscilloscope design our Capstone, and they came on board to write software for it. If y'all are watching this, thanks again for all the help. Bringing in other people made me realize my biggest mistake so far. I made all these modules in the order of the signal chain, which made sense to me. I also wanted to tackle the most interesting challenge first, the front end. But I should have done the complete opposite. That way I could have emulated sample data on the FPGA and given everyone the boards a year earlier, since to them it didn't really matter if it was real data or not. Speaking of real data, the first piece of software written for this project dumped a certain length of sample data into a CSV file. This would let me functionally test the complete system, end to end. I never thought I could be this excited by a spreadsheet, but seeing this pulse made me cackle like a mad scientist. I took this first victory as a chance to circle back to the front end. I made a new planning spreadsheet, studied a ton of Jim Williams app notes, and got to work. I decided to axe the 50 ohm termination spec and swapped over to a single attenuator. And instead of one op-amp doing everything, I used a JFET for AC couple signals and a op-amp for the DC component of the signal. Another op-amp was used to bias the JFET. This worked pretty well. No crazy peaking in the frequency response, and I can turn on the attenuator and see a scaled version of my input signal. No oscillations. I thought I could further improve the flatness of the response and get closer to my bandwidth target by combining the front-end modules together into one board. It worked well for flatness, but the bandwidth seemed to only be 260 megahertz. I called that good enough to move on, since everything actually functioned now. Later on, I realized, and this is a real trap, the 50 ohm output of the signal generator was forming a filter with the 12 picofarad input capacitance at exactly 260 megahertz. So this front end actually had more bandwidth on tap, but that's for another presentation. Now to address the weakest link, the new one, the throughput of USB 3 Gen 1. The Gen 2 part I had hoped for was still not released. I scoured the internet, but there was no good way forward using USB 3 Gen 2. So we're going full send into the Kafkaesque nightmare of USB 4, or Thunderbolt 3, or Thunderbolt 4. The common denominator is those all take PCIe and shove it through a USB-C cable, which I'm not sure if that's ethical, but here we are. Once you can readily see that in action in one of these external GPU enclosures, the chip that does this PCIe shoving is publicly available, but the datasheet is not. But that's still better than the USB Gen 2 situation. So I decided to make a PCIe card and stick it in a GPU enclosure until I could figure a way around this. Using an FPGA for PCIe is actually quite common, with many parts having dedicated blocks for it. There was one catch. All the cheaper parts only did PCIe Gen 2, while Thunderbolt and its ilk use PCIe Gen 3. Thankfully, they're backwards compatible, so it should work with a hit to the throughput. So I went looking for a dev board to test it out, and learned that anything with PCIe was just oddly pricey for adding a card edge connector to the board. And I found that the cheapest PCIe-capable boards were not physically PCIe, but M.2 cards. One adapter card later, and I was ready to take on more FPGA development. I put the card in the Thunderbolt enclosure, loaded up the example design, and transferred 8 megabytes in 7 milliseconds, a throughput of 1.1 gigabytes per second. We were in business. And so this project was reborn as ThunderScope, a Thunderbolt-connected oscilloscope. That was still a PCIe card, but I promise we'll get there eventually. Even though it looks very different, the majority of the design is just the modules from the old design shrunken down and placed on one board. With the exception of the big change, a new FPGA that only came in a BGA package and had to be connected to DDR3 memory, also only in BGA packages, and notoriously difficult to read. So I made all that future me's problem and used an off-the-shelf module to get this thing done in time for my university capstone project. The only other risky change was the 1 gigahertz clock generator, so I went for this incredibly easy to use all-in-one chip, the LMK61E2. Just give it power, and you can use I2C to configure it to output any frequency from 10 megahertz to 1 gigahertz. The FPGA design for this board was mostly smashing together Xilinx IP blocks and trying to reuse as much of my own Verilog as I could. ADC data gets turned into parallel data, much like last time, but then instead of going to an external USB 3 chip, it flows into this block called the data mover. The data mover then issues AXI bus writes to the DDR3 controller. AXI is the protocol these IP blocks use. And these writes increment over the whole address range and then loop back. On the other side, the XDMA PCIe core is checking the amount of data written and then reading from the DDR3, making the DDR3 into a circular buffer. The reason we even need this buffer, even though we're streaming out all the data, and ostensibly don't need it, is to soak up PCIe latency from the host system. I tried using just the FPGA's onboard memory, and this happened. There we are. Huh. The system interrupts caused by mousing over the triggering program caused enough inconsistency to overwhelm the 256 kilobyte internal buffer. We wouldn't need much more than a megabyte for this not to happen. But moving to DDR3 is way cheaper than getting an FPGA with that much memory built in. Hello? Yeah. There we go. While I was tinkering with the FPGA, my group members wrote a blazing fast trigger and a cross-platform UI in Electron. No groans. That's an improvement. And I wish I could explain it all here, but we are rapidly running out of time. The good news was, after furiously debugging it well past midnight, the day of the demo, it actually worked. And it was amazing. Thank you, thank you. It was amazing to see these waveforms on the screen for the first time. And it finally felt like this whole oscilloscope thing was coming together. Yep. But in reality, there was so much work left to do to get this remotely close to all the functions of a scope. And as we all graduated and started full-time jobs, the rest of the group moved on to other things. Those with personal copies of the prototype were super understanding and lent me their hardware to keep things going with. And I promised I'd return them as working oscilloscopes worthy of their lab benches. But now what? Here's the problem. I hadn't released any of this. I always imagined I'd release it all once it was capital D, done. In doing so, I'd missed out on the input of the open source community that I spent so long lurking in. Spent nights banging my head against problems that could have been spotted earlier, and slowed down the project as a whole. And now I was stuck. This project was simply too much for one person. So now was the time to fix that mistake. I couldn't just dump it all online and expect anyone to see it, or telepathically understand how things work so that they could help me. I had to document everything, and that meant I had to write things. I'm not kidding you when I said that was the hardest thing I've done this whole project. I entered the Hackaday Prize in 2021, and that helped give me the motivation to write detailed posts about the project up to that point. I shamelessly cribbed off of these for part of the talk, but you should go check them out for all the details. I also made a Discord server and overcame my aversion to social media enough to post about it on hardware Twitter, back when it wasn't half dead, and I got the project accepted by Crowd Supply too. It was truly amazing to see how many people were interested in this project. And with that interest came people who wanted to contribute. And thanks to my old group mates, I had 2 extra units to send them. The first contributor to the recently open source ThunderScope project was Frederick, who completely overhauled the code that talked to the hardware and made a bunch of utilities that made testing the boards so much easier. He's also the creator of the most popular board and software for making lightsabers. And it's all open source too. Go check it out if you ever want to feel like a real Jedi. Or Sith. I'm not judging.
I judge.
Shortly afterwards, Mark showed up and worked some truly arcane magic, AVX 512, SIMD, I don't understand these things, to make software triggering not only possible, but on par with doing it on the FPGA. He then built off of Frederick's ThunderScope hardware library to get the data over to his trigger, and even made a simple UI for testing. He's also an incredibly knowledgeable DC vault nut. He's got like 8 digits of precision on tap in his lab. It's crazy. And while discussing the project online, I got pointed to Andrew Zonenberg's project, GL-Scope Client. I recalled seeing something about it some time ago and wanted to check out what it could do. And was absolutely floored. It did protocols, FFTs, cursors, and it was all open source. The screen capture is actually Andrew using it with one of his wicked fast LaCroix scopes to measure the PCIe signals on a Rev 2 ThunderScope. This was a huge help to validate my janky solution for Thunderbolt. GL-Scope Client did all this from triggered data. So all we had to do was hook up ts.net to it, and it should work. But I didn't know where to start, so I asked Andrew for some more help, and he suggested the folks at Entropic Engineering, who made some scope drivers for Oscilloscope Client before. They are an engineering firm that loves working on open source stuff, so I asked them if they could contract with me to write a driver for ThunderScope, and they took it on. Special thanks to Lewis for the code wizardry and MP for their continued support of this project. And by all our forces combined, we had a solution that could process and display an immense amount of data. Every waveform drawn on the screen here is comprised of 40 megabytes of samples across these 4 channels. Only really using one, but 40 megabytes at full sample rate. And a new one is drawn on the screen at least 5 times a second. And with some improvements, we got that to 22 times a second. That's 90% of real time. We could get it to 100%, and that should mean absolutely no dead time between waveforms. It is buttery smooth. And on the FPGA front, Florent of Enjoy Digital contributed a LightX-based FPGA design. That's important because this LightX PCIe implementation is proven to be efficient enough to be able to only use the FPGA memory as a buffer without all that other crud happening from earlier. And that eliminates the power draw and cost of the DDR3. We haven't integrated his driver into the software yet, but the plan is to do so and help fund the creation of a Windows driver so that we can completely move from XDMA and make all of our FPGA stuff completely open source. And now, back to the hardware. How did I get Thunderbolt working in such a compact package? Well, I tried going through Intel for the NDA datasheet, but I'm just some schmuck unworthy of such enlightenment. Though if anyone here works at Intel, call me, please. Instead, I found the most commonly used Thunderbolt device, the M.2 NVMe adapter, and priced it out in bulk. And it wasn't that much worse than buying the chips and cables through distribution. So I decided to make a cursed M.2 adapter and mount the Thunderbolt board on the bottom of the main board. It's mechanically stable, and the PCIe signals come through just fine. So yeah, it works. Last things I want to show you that I couldn't cram into this 25-minute presentation. Probably should have taken the longer slot, eh? But I made a custom FPGA module to replace the off-the-shelf one, and Rev 2 and 3 of the baseboard. And soon, TM, we are doing a beta run of 10 more Rev 4s. And then after the beta run, we will release it to the public. And that's it from me. Thank you.